Welcome to the third outcome, all about sequences and series, the patterns sitting behind so much of business and finance. Spotting whether a list of numbers is adding on or multiplying up is the key that unlocks the right formula. A sequence is simply an ordered list of numbers, and a series is what you get when you add those numbers up. In this outcome, we'll learn to identify the main types, especially arithmetic sequences that grow by a fixed amount, and geometric ones that grow by a fixed multiple. For each type, we'll find the nth term and the sum of the terms, working real numbers through as we go. And the key skill is spotting whether a sequence adds a fixed amount or multiplies by a fixed ratio. Three terms will keep coming up. A term is a single number in the sequence, and the nth term is written u sub n. A recurrence relation is a rule that builds each term from the one before, like u sub n plus 1 equals u sub n plus 3. And a series is the sum of the terms, written s sub n for the total of the first n of them. Learning to read a sequence at a glance is half the battle. If you go 5, 8, 11, 14, adding 3 each time, that's arithmetic with a common difference. If you go 3, 6, 12, 24, doubling each time, that's geometric with a common ratio. Some follow other patterns entirely, like 1, 4, 9, 16, which are the square numbers, or 1, 1, 2, 3, 5, where each term is the sum of the previous two. Let's build a sequence from a recurrence relation. We're told u sub 1 is 5, and each next term is u sub n plus 1 equals 2 u sub n minus 1. Starting from 5, doubling and subtracting 1 gives 9. Do it again for 17, and once more for 33. So the sequence runs 5, 9, 17, 33, with each term leaning on the one before it. Here's a famous one, the Fibonacci sequence, defined by u sub 1 and u sub 2 both equal to 1, with each new term the sum of the two before it. So the third term is 1 plus 1, which is 2. The fourth is 2 plus 1, which is 3, then 5, then 8. Carrying on gives 1, 1, 2, 3, 5, 8, 13, 21, a pattern that turns up everywhere from sunflower heads to financial modelling. Let's name the main families. An arithmetic sequence adds a fixed common difference, d, each step, like 3, 7, 11, 15. A geometric sequence multiplies by a fixed common ratio, r, each step, like 2, 6, 18, 54. Some sequences are convergent, settling towards a limit, while others are divergent, growing without any ceiling, and knowing which family you're in tells you which formula to reach for. An arithmetic progression adds a common difference each step, and its nth term is u sub n equals a plus n minus 1 times d, where a is the first term. Take 3, 7, 11, 15. Here a is 3 and d is 4. To find the 10th term, we work out 3 plus 9 times 4, which is 3 plus 36, giving 39. The terms climb in a straight line, one steady step at a time. Now let's total up a whole run of terms. To sum the first 20 terms of 3, 7, 11, 15, we use s sub n equals n over 2, times the quantity 2a plus n minus 1 times d. Putting in 20 terms, with a equal to 3 and d equal to 4, gives 10 times the bracket 6 plus 76. That's 10 times 82, which comes to 820. Sometimes you know the value and want its position instead. In the same sequence 3, 7, 11, 15, which term equals 43? We set the nth term formula equal to 43, so 3 plus n minus 1 times 4 equals 43. That leaves n minus 1 times 4 equal to 40, so n minus 1 is 10 and n is 11, so 43 is the 11th term. The counting numbers 1, 2, 3, and so on form an arithmetic sequence with first term 1 and common difference 1. Their sum has a lovely shortcut. S sub n equals n times n plus 1 over 2. To add every number from 1 to 100, we work out 100 times 101 over 2, which is 10,100 divided by 2, giving 5,050. That's the trick the young Carl Friedrich Gauss famously spotted in class. A geometric progression multiplies by a common ratio each step, and its nth term is u sub n equals a times r to the power n minus 1. Take 2, 3, 4.5, 6.75. Here a is 2 and the ratio r is 1.5. For the fifth term, we work out 2 times 1.5 to the fourth power, which is 2 times 5.0625, giving 10.125. When r is bigger than 1, the terms grow faster and faster. That's exponential growth. To sum a geometric series, we use s sub n equals a times r to the n minus 1 all over r minus 1 when r is bigger than 1. Let's add the first 6 terms of 4, 8, 16, where a is 4 and r is 2. That's 4 times 2 to the 6th minus 1 over 2 minus 1, which is 4 times 63 over 1. So the sum is 4 times 63, which is 252. Something remarkable happens when the ratio sits between minus 1 and 1. The terms shrink towards 0, and the whole infinite sum settles on a finite limit. The sum to infinity is s infinity equals a over 1 minus r, with a equal to 8 and r equal to 0.5. That's 8 over 1 minus 0.5, which is 8 over 0.5, giving 16. The running totals, 8, 12, 14, 15, creep up towards 16 but never quite reach it. Here's where geometric sequences pay off in the real world. Say you save £100 and it grows by 5% a year. Multiplying by 1.05 each year is a geometric progression. So the value after n years is 100 times 1.05 to the power n. After 3 years, that's 100 times 1.05 cubed, which is 100 times 1.157625, giving £115.76. Compound interest, loan repayments, and population growth all follow exactly this pattern. Let's set the two side by side. An arithmetic progression adds a common difference d, with nth term a plus n minus 1 times d, and a sum of n over 2 times 2 a plus n minus 1d. It grows in a straight line and has no sum to infinity. A geometric progression multiplies by a common ratio r, with nth term a times r to the n minus 1, and a sum of a times r to the n minus 1 over r minus 1. And it only has a sum to infinity when the size of r is less than 1. So how do you choose? Your first test is to check for a common difference by subtracting terms, or a common ratio by dividing them. A constant difference means arithmetic. A constant ratio means geometric. Use the nth term formula when you want a single term without listing them all, the sum formula for a running total, and the sum to infinity only when a geometric series is converging. Whatever you do, pin down A and either D or R before you pick a formula. To recap the third outcome, a sequence lists terms, a series adds them, and a recurrence relation defines each term from the one before. Arithmetic progressions add a common difference. Geometric progressions multiply by a common ratio, and each has its own nth term and sum formulas. The counting numbers add up to n times n plus 1 over 2, and a geometric series has a sum to infinity only when the size of r is below 1, which is exactly what makes compound growth such a useful real-world example. And that closes the outcome on sequences and series, from spotting the pattern to summing it and, in the geometric case, adding infinitely many terms. Do keep practicing the identification step first, since choosing arithmetic or geometric correctly makes everything after it straightforward. To go further, the reading list suggests core maths for advanced level and the CGP revision guides, with extra practice on Maths Genie, Dr. Frost Maths, and Khan Academy. And the unit's ebooks on Moodle are always there if you'd like more worked examples.